We're still dealing with a clock that is right only 2 times a day. It's not 10 o'clock, but it is time to start. So um, today we're going to continue our discussion of the Wittig reaction. Then we're going to learn about imines and enamines, two classes of compounds that we can synthesize from aldehydes and ketones. And then we're going to talk about hydrates and acetals, which are two closely related compounds that also are synthesized from aldehydes and ketones. So we need to first address an issue of the Wittig reaction that is kind of glossed over in the book, and that is stereochemistry of the alkene that is produced. We know that some alkenes can have E and Z isomers. These are diastereomers of each other. The book gives you an example where the E isomer is major and the Z isomer is minor. And unfortunately, that's the exception rather than the rule. It is possible to manipulate the reaction conditions to favor the E isomer, but generally speaking, with most Wittig reagents, the Z isomer is going to be the major product, as I've drawn for you here on the board. Okay. The reason for that is unfortunately beyond the scope of this class. There is an advanced organic chemistry class called Chem 553, which is a really good class. The students who take it are a mixture of first-year graduate students who are just starting their PhD here at BYU, and undergraduate seniors who are planning on going to graduate school elsewhere. So if you're in that latter category, when you become a senior, you should take Chem 553. It's a fun class. And in that class, we actually learn why the Z isomer is the major product of most Wittig reactions. There's one type of Wittig reagent that favors the E isomer, and that is a Wittig reagent known as a stabilized ylide or a conjugated ylide. We have our two different resonance structures that we can draw of our Wittig reagents. We have the one with the negatively charged carbon that has a lone pair. We have the other one, which is shown here on the screen, with a carbon-phosphorus double bond. If that lone pair or that double bond is conjugated either to another alkene or to a carbonyl group, then that conjugation stabilizes the Wittig reagent, and we refer to it as a stabilized ylide. So whenever we are using a stabilized ylide, the E isomer is going to be the major product, as evidenced by this reaction here. So this is a good example in the book. Here we have a stabilized ylide conjugation of the carbon-phosphorus double bond with numerous alkenes in this case. And you see that the new alkene that is formed is indeed E. It's in the E configuration. Okay? So what happens, again, without going into details, what happens is that with the stabilized ylide, the mechanism changes a little bit. Okay, we're not going to discuss it. We're just going to learn the standard mechanism we learned last time. But there's a slight modification that results in favoring the E isomer with a stabilized ylide. So we're just going to have to memorize this in this case because the explanation is beyond the class. Normal ylides, normal Wittig reagents will favor Z. Stabilized ylides, where we have conjugation, is going to favor E. Any questions about that? Okay. So another thing we need to be able to do with the Wittig reaction is use it in a retrosynthetic fashion. We need to be able to look at an alkene and decide which combination of an aldehyde or ketone and a Wittig reagent would produce that alkene. If the alkene is not symmetrical, then there's going to be two combinations of an aldehyde or a ketone and a Wittig reagent that will make that alkene. So we need to ask ourselves, would both of those possibilities be equivalent to each other, or would one of those possibilities be better, give a better outcome than the other? So I'm going to pose that question to you in the form of an iClicker question. So let's get our iClickers out. We have an alkene drawn on the screen. Of course, there's only two possible combinations of Wittig reagents and aldehyde or ketone that will make that alkene. So first you have to identify which of the four choices here will actually work. And then the way we phrase the question partially answered the question I posed to you, which is that one of those two methods is going to be better than the other. So go ahead and talk to your neighbors and decide which of the two possible methods of making this alkene via a Wittig reaction will be best. And I'll give you a hint. You're going to want to consider the pathway used to synthesize the Wittig reagent. Okay, that's where you're going to find the difference in the two possibilities, is the reactions used to synthesize the Wittig reagent, which we talked about at the end of class on Monday. So go ahead, talk to your neighbors, and answer the question. All right, let's try to get our final answers in here in the next 15 or 20 seconds. All right, going once, going twice. Any more answers? We're stuck on 26, it looks like. Okay, we'll go ahead and stop that. Okay, so first of all, which of these four choices would actually work to make this alkene? Which of the two choices would work? Or which two of the four choices would work? Sorry. Yes. B and C. Yeah? So we can eliminate A and D. They would give different alkenes. We need to count carbons in order to figure that out. So we count carbons. We arrive at B and C. Okay. It looked like there was some debate based on the choices that I saw between B and C. If you chose C and you're willing to explain why, please raise your hand and tell us your reasoning. Anybody willing to take a stab? Yes, please. Okay. Good. Okay, exactly. So the first step in synthesizing the illid or the Wittig reagent involves an SN2 reaction with an alkyl halide and triphenylphosphine as the nucleophile. We know that SN2 reactions are faster and in most cases higher yielding with a less substituted alkyl halide. So when you have a choice, you want to choose the combination that has the less substituted Wittig reagent, because that's going to be synthesized from the less substituted alkyl halide. So if we look at C, that would come from a primary alkyl halide. You would have had your halide here. And if we look at B, it would have come from a secondary alkyl halide. So you could still do it through B, but it would be a longer reaction and it would probably be a lower yielding process as well. Okay, so when given a choice, choose the combination that has the less hindered alkyl halide. You'll get a better result. Any questions? Okay, so let's compare the Wittig reaction to other methods of synthesizing alkenes that we've learned previously. We've learned that you can dehydrate alcohols to make alkenes. And in chapter 20, we learned that you can make alcohols by adding Grignard reagents or organolithiums to ketones. So we could start with cyclohexanone. We could add a Grignard reagent followed by water, giving us this tertiary alcohol. Then we treat that tertiary alcohol with sulfuric acid. That's going to dehydrate, but we're going to get two products. Okay, we have the major product, the more substituted alkene, Zaitsev's rule. The minor product is over here. But what if we want the minor product? Well, this plays into the advantage of the Wittig reaction, which is that the Wittig reaction will give you a single constitutional isomer in all cases. You know where that carbon-carbon bond of the alkene is going to be. It's going to be between the carbonyl carbon of your aldehyde or ketone and the negatively charged carbon of your Wittig reagent. Okay? So if we react cyclohexanone with this, our simplest Wittig reagent, we're going to get this as our only product. So that's the biggest advantage of the Wittig reaction, is that we get only one constitutional isomer from the reaction. Whereas if we're performing a dehydration or other eliminations, we typically get multiple constitutional isomers, usually a major and a minor product. Okay? So that's why the Wittig reaction is widely used. That's why Georg Wittig ended up winning the Nobel Prize for discovering it. Any questions about Wittig reactions? Okay, let's talk about reactions of carbonyl compounds with amines, specifically with primary amines. Okay, so a primary amine is an amine that has one alkyl group, one R group attached. So it's going to have NH2, going to have two hydrogens and one R group attached. And we can react a primary amine with an aldehyde or a ketone. The book tells us that we need mild acid presence. That's the book's way of saying we need a pH somewhere in the range of 4 to 5. We'll explain why this narrow pH window is critical in a moment. There's two ways to accomplish that. You could use a small amount of a strong acid, or you could use larger amounts of a weak acid. But you need to be in this pH range for the reaction to work properly. We know that ammonia is a strong nucleophile. Primary amines are kind of on the border between strong and weak nucleophiles, but they're strong enough nucleophiles that they're able to attack carbonyl groups. And we would generate a species looking like this. This is known as a carbanolamine. Okay. The ol is referring to the alcohol, the amine is referring to the nitrogen. But we're going to put this species in brackets because it is not the final product of the reaction. We're going to eliminate water from this carbanolamine species. And we're going to generate a molecule with a carbon-nitrogen double bond known as an imine. Okay. So an imine resembles a carbonyl compound. We have sp2 hybridization of the carbon and the nitrogen, trigonal planar geometry. We know that our carbonyl compounds, aldehydes and ketones, are electrophiles. Would we expect an imine to be more electrophilic or less electrophilic than an aldehyde or ketone? More or less electrophilic? Okay, less, why? Nitrogen is less electronegative than oxygen. So the carbon-nitrogen double bond is less polarized than the carbon-oxygen double bond, leading to a smaller partial positive charge on the carbon of an imine. So an imine will be an electrophile, but not as good of an electrophile as an aldehyde or a ketone. Okay? So let's discuss how imines are formed. And our textbook normally does an excellent job of explaining mechanisms. But unfortunately, this case is one of the deficiencies where it actually skips over some key steps in the reaction mechanism. So please pay close attention and take good notes, because we are not going to skip the steps. We're going to discuss each and every step in the mechanism of imine formation so that we can understand what's going on in the reaction. Okay? So we will start with our aldehyde or ketone, right? One of these R groups could be a hydrogen. They could both be alkyl groups. We're going to react that with our primary amine. Our primary amine is a strong enough nucleophile that it can attack the carbonyl carbon of our aldehyde or ketone. We're going to use our equilibrium arrows because, as we'll discuss in a moment, imine formation is reversible. So each of these steps is reversible. So here's the product that we obtain. Okay. So here's where the book skips important steps. The book just writes proton transfer over an arrow and goes from this to an intermediate that's 2 steps ahead. Okay, we're not going to do that because the proton transfers are important steps, and it's important to know what's going on in those proton transfer steps. So please make sure that you draw out the proton transfers when you are drawing this mechanism. So we have a certain concentration of acid present because we're using mild acid. We have that pH 4 to 5 range. So we have some H3O plus present in the reaction mixture. And we can protonate our negatively charged oxygen with our H3O plus. Okay. And then when we use H3O plus to protonate that oxygen, we now have water present. And that water can deprotonate the positively charged nitrogen. So that's how we get to our carbanolamine intermediate, by protonating the oxygen with H3O plus, deprotonating the nitrogen with water. Okay. You might ask, why can't we just use the oxygen to deprotonate the neighboring nitrogen? That would save us a step. You could do that, but the problem with that is it would involve a 4-membered cyclic transition state, which is going to be strained. That's going to raise the activation energy of that transition state and make that process slower than the intermolecular process. Proton transfers between 2 heteroatoms, we've mentioned previously, are the fastest intermolecular steps that we have. We're transferring the smallest nucleus possible from one heteroatom to another. So that happens very rapidly. So these 2 steps happen faster than the time it would take to organize that strained 4-membered transition state to do that proton transfer in an intramolecular fashion. Okay, so it's better to draw the mechanism in the way that we've drawn it here. We can have 4-membered cyclic transition states. We have one in the Wittig reaction that we just talked about, but there's a special driving force in that case. We're forming that very strong phosphorus-oxygen bond. Okay, so if you're going to have a four-membered cyclic transition state, usually you need some sort of special driving force to make that transition state low enough in energy to have the reaction occur. So no four-membered cyclic transition state in this case, two intermolecular proton transfer steps to get us to our carbonylamine species. Any questions so far? Okay. So as we go on from here, right, when we use water as a base, that's going to generate H3O plus again. So we can protonate the oxygen. That's going to release water. And that's going to generate an oxonium ion. Okay. So we have a positive charge on oxygen. Water, we know water is a good leaving group. So now that water can depart. And we're going to use the lone pair on the adjacent nitrogen to help it depart. Okay. That's going to give us an intermediate known as an iminium ion. Okay. This is called an iminium ion. Okay. It's a resonance stabilized species. You can draw a minor contributor without this double bond and a positive charge on the carbon. But this is the major contributor, so I prefer to draw the mechanism in a way that involves the major contributor. Okay? And we eliminated out water in this step, so we can use our water molecule to deprotonate our iminium ion and form the imine product. And we've regenerated our acid. Okay? So this is how we form an imine. You'll notice that each step in the mechanism is a proton transfer, with the exception of our nucleophilic attack and our elimination of water. So we have those two steps. Every other step is just a proton transfer, an acid-base reaction. Okay? So understanding acid-base chemistry is critical to understanding the mechanism of imine formation. Okay? Any questions? So this is an equilibrium process. What could we do to manipulate the equilibrium if we wanted the imine to be the major product? What could we do? Think about Le Chatelier's principle. Okay, we could remove a product. We could remove water. That's easier said than done because we're using water in some of these steps. So usually the most practical way to do it is to have excess of one of the reactants. So if we have excess amine, then that's usually going to cause us to form the imine from our aldehyde or ketone. Okay. If you wanted to run it in reverse, if you wanted to hydrolyze the imine to generate the aldehyde or ketone, what could you do? What would be your reagent, your nucleophile that you would use if you were going to hydrolyze the imine? You'd be reacting water, right? Water is one of the products. You'd be reacting water with the imine. So if you use excess water, if you expose an imine to excess water at pH 4 to 5, then you're going to convert that imine into the aldehyde or ketone. Okay? So an important question about this reaction is, why do we need this narrow pH range? Why do we need it in the 4 to 5 range in order to work? Well, we know why we need acid. We need acid present to facilitate these proton transfers. Our first proton transfer is from acid to this negatively charged oxygen. So we need a certain amount of acid in the reaction mixture. But what would happen if we had too much acid? Our primary amine is also a base. And so we have an acid-base equilibrium involving our primary amine, where we protonate that nitrogen. Okay. So the higher the concentration of acid, the more of the ammonium ion, the conjugate acid of our amine, we have in solution. Is the ammonium ion going to be a nucleophile? No, it has no lone pairs. It's not nucleophilic. So if we have a lot of this and not very much of this, we're dead in the water. The reaction's not going to work. Okay? We're always going to have some of this because we always have some acid present. But if we limit the amount of acid, we have a smaller amount of our ammonium ion present and a larger amount of our primary amine, and we're able to form the imine. So we're kind of walking a tightrope. We have a fine balance between having enough acid present in the solution to allow the reaction to proceed, but not too much acid that would protonate the primary amine and shut the reaction down. Questions? Yes? You could use either one, but generally speaking, your ketone usually has more carbons in it than your amine. Usually it's more expensive as a result. And so you typically would use the cheaper of the two reagents in excess, which usually is the amine. Okay, good question. So imine formation is important in biochemistry, specifically in the chemistry of fission. In chapter 16, in our recorded lectures we had at the beginning of the semester, we talked about this process of how rhodopsin, which is formed by the conjugation of retinal with a protein known as opsin, when it absorbs visible light, an electron is promoted from a bonding to an anti-bonding molecular orbital, weakening the pi bonds sufficiently that you're able to break and isomerize that pi bond in the excited state. And then when the molecule relaxes down to the ground state, we have a trans double bond instead of a cis double bond. And that change in shape due to that isomerization is recorded as a nerve impulse that our brain converts into vision. Okay, we went over that in chapter 16. Really cool chemistry. The linkage between the retinal and the protein is an imine. So the aldehyde of retinal reacts with a primary amine from the protein. It's coming from a lysine amino acid, the side chain of lysine, and it forms an imine. Okay, so that imine linkage is critical to joining retinal with opsin to form the rhodopsin molecule. Okay, so it plays a role in vision. All right. So another question you might have is, why does it have to be a primary amine? What would happen if we reacted a secondary amine with an aldehyde or a ketone? And the answer is they would react, but they would not give an imine. They would give a different product. And we also need at least one alpha hydrogen on our carbonyl compound. So we'll draw it like this. All right, these groups could be alkyl groups, they could be hydrogens, it doesn't really matter, but we have to have at least one alpha hydrogen in order to react our carbonyl compound with a secondary amine. So a secondary amine has two alkyl groups attached to the nitrogen. They can be the same or different. For simplicity, I'm going to draw them as the same alkyl group. So if we use our mild acid and we have a secondary amine reacting with aldehyde or ketone, our first intermediate's going to be the same. we're going to generate, whoops, let me draw it that way. We're going to generate that carbanolamine analogous to the carbanolamine that we formed with our primary amine. We're also going to eliminate out water, but we're going to get a different product. Instead of getting an imine with a carbon-nitrogen double bond, we're going to form a molecule known as an enamine. Actually, we just need one prime here. We're going to generate a molecule known as an enamine, where we have a carbon-carbon double bond. We have an alkene, and we have a nitrogen bonded to that alkene. So the ene in this name is referring to the alkene. The amine is telling us that we have a nitrogen bonded to that alkene. Okay? So we'll explain why we get an enamine as opposed to an imine in a moment. Another factor, another issue we have is the number of types of alpha hydrogen. So if we have an aldehyde, we're only going to have one type of alpha hydrogen. If we have a ketone, depending on the type of ketone we have, we might have one type or two types of alpha hydrogens. This reaction works best with symmetrical ketones that only have one type of alpha hydrogen because then there's only one constitutional isomer of our enamine that we can form. Okay, so here's an example of that. We've used cyclohexanone. We're reacting it with dimethylamine. And because these alpha hydrogens are equivalent to each other, there's only one enamine product that can be formed from that reaction. Okay? So this mechanism is very, very similar. It's actually identical to the mechanism of imine formation until we get to the last step. Okay? So we're going to look at it on the screen. First step is the same, amine attacking our carbonyl carbon. Then we have our proton transfers. Please do not skip the proton transfers when you're actually drawing this mechanism. But that gets us to the carbanolamine when we have those two proton transfers, protonating the oxygen with H3O+, deprotonating the nitrogen with water. Okay? Next step is going to be the same. We're going to protonate the oxygen with H3O+. And the step after that is also the same. We're going to be eliminating water from that intermediate. So now we've made it to our iminium ion. But there's a difference in this iminium ion compared to the iminium ion that we had with our primary amine. When we used a primary amine as our nucleophile, we still had a proton on the nitrogen of our iminium ion. It is right here now. Okay? And we're able to deprotonate the nitrogen of the iminium ion to generate the imine product. When we're using a secondary amine as our nucleophile, we've already deprotonated the nitrogen. We deprotonated it up here. So now we have an iminium ion with no proton on the nitrogen. So we cannot deprotonate the nitrogen. If we have an alpha hydrogen, at least one alpha hydrogen, we can deprotonate that instead. You see the curved arrows we would draw? That gives us a carbon-carbon double bond. We push the electrons from the carbon-nitrogen double bond back onto the nitrogen, and that gives us our enamine. Okay, any questions? So, yes. Good. It could. You also might reach a point where steric hindrance would play a role, but yeah, so there might be differences there in the rates, but I'm not entirely sure. The key difference, though, the key thing we want to focus on is very nicely summarized in this figure right here, showing us reaction of cyclohexanone with a primary amine and a secondary amine. In both cases, we generate iminium ions. And the mechanism of how we form those iminium ions is identical. But once we get to the iminium ions, then the routes diverge. with the primary amine, we still have a proton on our nitrogen, so we can deprotonate that and generate an imine. We cannot form an imine when we have a secondary amine, no proton left on the nitrogen. So we have to deprotonate the alpha proton, giving us an enamine. Okay? So what would we use enamines for? Why would we want to make enamines? They're actually really good nucleophiles. Excuse me. We know that alkenes are nucleophilic. We've used alkenes as nucleophiles in many reactions that we learned last semester. If we attach a strong electron donating group to our alkene, that makes it an even better nucleophile. Okay? So we can react enamines with electrophiles like this. Okay? Alkyl halides are good electrophiles in this reaction, for example. And that gives us an iminium ion intermediate. And then usually we hydrolyze that iminium ion intermediate. We add water, mild acid, and if we use excess amounts of water, then that's going to give us our ketone. Okay. So this is a way of, and then we'd have dimethylamine as well as a byproduct. So this is a way of attaching an electrophile to the alpha carbon of a ketone. We convert the ketone to an enamine. We react the enamine with an electrophile, and then we hydrolyze the iminium to get the ketone. We're going to learn other ways in chapter 23 to attach electrophiles at the alpha carbon of carbonyls, but this is one way of doing that. Okay. So we can hydrolyze our iminium ion intermediate we get from this process. We're also able to hydrolyze our imine or our enamine itself, much like the imine, if we react it with water in the presence of mild acid. Then we're going to reverse. We're just going to go, and remember we also learned last semester that when we have an equilibrium process, we encounter the same intermediates and transition states just in opposite directions. And so we would just have the reverse mechanism of enamine formation in the presence of excess water and mild acid, giving us our ketone and our dimethylamine. Okay? Any questions about making enamines or hydrolyzing enamines? All right. So our amines are kind of on the border between strong and weak nucleophiles. Let's talk about what happens when we react a weak nucleophile, something that's really a weak nucleophile, with an aldehyde or a ketone. So our most common weak nucleophile is water. And we can react water with an aldehyde or a ketone. Because it's a weak nucleophile, we need a catalyst. That catalyst can either be base or acid. And when we add water to a carbonyl compound, we generate something known as a gem-diol. Gem stands for geminal. Geminal is a term we learned last semester, which means on the same carbon. So if we have a diol on the same carbon, it's a gem-diol. There's another name for this species. We can call it a hydrate. Because we've hydrated our alkene, or we've hydrated our carbon-oxygen double bond. And we actually learned about hydrates last semester as intermediates in oxidation reactions from chapter 12. We learned that when you oxidize a primary alcohol to an aldehyde, when you have water and acid present, like here, you can form a hydrate, and then you can oxidize that hydrate to a carboxylic acid. Okay, so We went over that. We went over the hydration process, briefly went over the mechanism, and now we're going to go over it in a little more detail. But first, let's talk about the equilibrium. The equilibrium between the aldehyde or ketone and the hydrate. In most cases, that equilibrium strongly favors the carbonyl compound, the aldehyde or the ketone. In most cases, it's much more stable than the hydrate. Here on the screen, we have some examples. So acetone, this is typical of ketones. Less than 1% of the hydrate will be present at equilibrium. And with most aldehydes, it's going to be comparable, maybe a couple percent. But then with acetaldehyde, where we have a methyl group, we slightly favor the hydrate over the aldehyde. And then with formaldehyde, our smallest aldehyde, we strongly favor the hydrate. Okay? So what we see here is as we add alkyl groups to our carbonyl, here we have 0 alkyl groups, here we have 1 alkyl group, here we have 2. As we add those alkyl groups, we're favoring the carbonyl compound at equilibrium over the hydrate. Why? And there's two correct answers to this question. So that increases your chances of being right if you raise your hand and give us an answer. So why does increasing alkyl groups favor the ketone or the carbonyl compound over the hydrate? Any guesses? Yes. Okay. Yeah, more alkyl groups makes it more sterically hindered. How many groups are there on a carbonyl carbon in a ketone? How many groups attached to that carbon? sp2 hybridized? Has 3 groups, right? How many groups attached to the carbon of a hydrate? 4 groups, right? So those 4 groups are closer together, tetrahedral geometry, smaller bond angles. So you have less steric hindrance in a ketone than you do in a hydrate. So as you add alkyl groups, you're destabilizing your hydrate because of sterics. Okay? So we have one steric explanation, and that was correct. Is there an electronic reason why the ketone would be favored over the hydrate with more alkyl groups? There is. Anybody want to tell us? Yes, please. That's right. We have a partial positive charge on that carbonyl carbon. Alkyl groups donate electrons to that partial positive charge on the carbonyl carbon. And so that makes the ketone more stable than the aldehyde, which in turn is more stable than formaldehyde. There's no electron donating groups on formaldehyde, so that destabilizes formaldehyde and means that it exists presumably almost completely in the hydrate form. Okay? So with formaldehyde, we have destabilization of the carbonyl compound combined by no steric hindrance in the hydrate, and so the hydrate is favored there. Okay? So a combination of steric and electronic reasons in most cases favor ketones over hydrates, but certain aldehydes you do have substantial amounts of the hydrate. So there's a special aldehyde. So with acetaldehyde, we see that the hydrate is favored. If you lengthen the chain, if you make this methyl group longer, ethyl or so forth, then you're going to favor the aldehyde. So most aldehydes are favored over their hydrates. But there's a special aldehyde I'll draw for you here. This is called chloral, that strongly favors the hydrate. I don't have the numbers, but it's probably somewhere on the order of 99 to 1 or even greater. And this is known as chloral hydrate. Okay? So why would the hydrate of chloral be favored more strongly than the hydrate of acetaldehyde? Why the hydrate more favored over the aldehyde than what we have here with this ratio? Yes, please.
Because chlorines are withdrawing.
We have an inductive effect. We have these three bonds polarized towards our electronegative chlorines. That gives us a carbon with a partial positive charge adjacent to another carbon with a partial positive charge. Okay? So to eliminate that destabilization, water adds, and we end up with the hydrate. Okay? There's another name for chloral hydrate. It's known as Mickey Finn drops. Okay? Have you ever heard of the term slip someone a Mickey? If you watch old gangster movies, someone in the last class said that Seinfeld used that term in one of their episodes, to slip someone a Mickey. It originates with a bartender in Chicago whose name was Mickey Finn around 1900. It turns out that chloral hydrate is a sedative. It dissolves in water. You add it to water or water-based drinks, it will dissolve, so you don't know what's in there. You drink it and it knocks you out. So patrons of this bartender, Mickey Finn, would tend to wake up, have no idea how they got where they were or what happened to them, and they'd be missing their wallets. And it turned out that he'd been slipping chloral hydrate into their drinks. They'd been going unconscious, and he'd been robbing them while they were unconscious. Okay, so the term "slip someone a Mickey" was used in gangster movies back in the 40s and 50s for putting chloral hydrate in somebody's drink, and I guess it's used in other TV shows as well. So if you hear that phrase, that's what it's referring to. Okay, so let's briefly discuss the mechanism of hydrate formation. And we're just going to look at it on the screen because we actually went over it last semester briefly. And it's simple compared to some of the other mechanisms we've looked at. We have to have either base or acid catalysts. So there's two different mechanisms. In base, our hydroxide is a strong nucleophile, so that will attack our carbonyl carbon. And then our water protonates the oxygen, giving us our hydrate, regenerating our base. That's why it's catalytic in base. Okay? In acid, our nucleophile is going to be water. Water is a weak nucleophile. It's not going to attack the carbonyl, the neutral carbonyl. So we have to protonate the carbonyl to make it more electrophilic first. So we do that. We protonate the carbonyl oxygen, get a resonance stabilized species. We could have the water attack either of these resonance structures. It doesn't matter. I tend to like to use the major contributor. The book here is showing us attacking the minor contributor. Either way, you get to the same intermediate, which you now have to have a third step to deprotonate that, getting our product and regenerating the acid catalyst. Okay? Any questions about that mechanism? So our other type of weak nucleophile that we have other than water is an alcohol. And alcohols can also react with carbonyl compounds, generating species that are similar to hydrates. So we're going to need two equivalents of our alcohol. Or as we'll learn on Friday, sometimes we use a diol, one equivalent of a diol. We're going to use toluene sulfonic acid in this reaction. We're going to use benzene as a solvent, and we're going to heat up the reaction mixture. We'll explain why we're doing all that in just a moment. But we'll get a species looking like this. It looks like a gem diol or a hydrate, but it has two alkoxy groups as opposed to OH groups, and that's known as an acetal. Okay? This is an equilibrium process. I forgot to write that we also form water as a product. So this particular equilibrium is easiest to manipulate, to push it to the right, by removing water. And we have a special way of removing water from this reaction. It works really well. It's using a device known as a Dean-Stark trap. That's this species right here. And it relies on a species called an azeotrope. Does anyone know what an azeotrope is? It's a term you may have learned in general chemistry. It refers to a constant boiling mixture. So sometimes when you mix two liquids together, they will boil. Instead of boiling at their two different boiling points, they will mix and they will boil at a single boiling point, which is lower than the boiling point of the two liquids on their own. Benzene is essential as the solvent in this reaction because benzene and water form an azeotrope. The azeotrope of benzene and water boils at about 70 degrees, lower than the boiling points of water and benzene separately. So if you heat your reaction mixture hot enough that you're not just boiling off the benzene, but above 70, so you're boiling your benzene in your water, as your water forms and mixes with the benzene, it's going to boil off. Usually you need foil coating this tube to keep it from condensing in the tube, because you want the vapor to travel up to this water condenser, cool and condense, and drip down. After it condenses, it separates. Benzene and water are not miscible. They don't dissolve each other. Water is more dense than benzene, so water is going to be at the bottom here. That's why you have a stopcock on this device. You can drain out the water, and that's how you remove it from the reaction mixture as it forms. Okay? You fill up this tube, benzene drips back in. That's fine if the benzene drips back in, as long as you're draining out the water. Okay? So a very, very simple but effective way of removing water from the reaction mixture, relying on this property of azeotropes, a constant boiling mixture. Last question I'll ask you for the day. Why do we use toluene sulfonic acid in this reaction? There's a key property it has that I mentioned previously that allows us, or that requires us to use it instead of other acids in this reaction. Think about its structure and think about its solubility properties. And think about the solvent we're using in this reaction. Okay, Wendell? It's soluble in organic solvents. So toluene sulfonic acid is very similar to sulfuric acid, but because it has that toluene ring attached, it's soluble in organic solvents. So we need, since we're using organic solvents in this reaction, we need an acid that dissolves in organic solvents. Okay? So we're going to draw the mechanism of this reaction on Friday. We'll finish off chapter 21 on Friday, and then we'll start chapter 22.